This video is going to talk through the Chapter 11 handout, which is posted in the Blackboard course materials. The focus of this handout is to learn how to use R to work with probability models, so I'm going to switch into RStudio in the cloud. Okay, so here we are in RStudio in the cloud. The first thing I want to do when I'm in RStudio is I'm going to require Mosaic, as I always do when I'm working for this course. And then we're going to start learning how to work with the probability models. So first of all, we're going to focus on how to generate random draws from a probability model. And the way that we're going to do this is by creating an object. I'm calling mine here draws, right? That we can use to store the randomly generated values. Then we use the letter R as the beginning of the function name is going to tell us that we are randomly generating. And then the model name is going to be added to the R. That's going to tell us which of the probability models we are randomly generating draws from. Now remember, we have a table from the slides with all of the probability models on it. I'll look at that in a sec. There it is. So this tells us for whatever probability model we want to use, tells us what we would like to, what model name we need to put in. And it also tells us what parameters need to be specified in order to do the calculations in R. So this is a good table to keep handy while you're working through this material so that you can quickly refer to what you need to put in for each model. So once we've got the R and the model name, that's going to be the name of our function, then we need to specify the sample size, how many random draws we are taking from this distribution. And we also need to specify the parameters that are relevant for that particular model name. So for example, if I want to generate 500 random draws from a normal distribution with a mean of 100 and a standard deviation of 15, I make an object, draws, that I'm going to use to store the randomly generated values. I do R and then norm for the normal distribution. Now I tell it how many draws I want, 500. And then for the normal distribution, I need to specify the mean, which in this case is 100, and the standard deviation, which in this case is 15. That generated the draws for me. If I run it. And now if I want to take a look at the distribution of that, I can use the histogram function and make a histogram of the draws. And I'll just put a little title on it. Whoop. Main equals normal, mean equals 100, standard deviation equals 15, just so I know what I'm looking at. And there we go. Now you can see these are randomly generated values, so if I run these lines again, I get a distribution that looks slightly different because I'm getting a different set of randomly generated values. So we're going to start off by doing a little exploration with the binomial distribution. So first I'm going to generate 1,000 draws from a binomial distribution. So R, the binomial distribution's model name is BINOM. I want 1,000 draws. And then for the binomial, I have to specify the size, which is my N number of trials. So I've got 10 trials. And P is the prob, and that's 0.3. So now I can generate the draws from this distribution and take a look at what that distribution looks like. binomial n equals 10, p equals 0.3. Here we go. Now it looks a little funny and gappy, and that's because of the number of breaks that R chose to put in here. So I'm just going to change that. I'm going to type comma, breaks equals 10, and we get something that's a little bit easier to look at. So we can see that this binomial distribution with n equal to 10 and p equal to 0.3 is a bit skewed to the right. We are going to take a little bit of time to look at how the shape of this distribution will change if we change the value of p, the probability of success on each trial. So I'm going to start by copying and then pasting down here the code that I just used, and I'm going to change the probability of success from 0.3 to 0.5. So let me just change that value, and I'll change it in the title too so that I can keep track when I'm looking back at these. So changing p to 0.5, you can see gives me a much more symmetric looking distribution. And changing p again from 0.5 this time to 0.7. Whoop. What happened? I don't think I ran it. There we go. Gives us a distribution that is, again, skewed a bit, but this time to the left. So when I've got a relatively small number of trials, like n equals 10, then when I have p that is close to 0.5, I'm going to end up with a distribution that's relatively symmetric. But when p is far away from 0.5, I'm going to end up with a distribution that is skewed. If p is less than 0.5, it will be skewed to the right. For instance, if I put in p of 0.1 here, just change it for a minute to 0.1, we should see something more strongly skewed to the right, and we do. If the probability of success is more than 0.5 and getting up close to 1, something like 0.9, then I should get something that's strongly skewed to the left, which I do. And again, if I were to put in something that's close to 0.5, something like, say, 0.53, got an extra decimal point there, whoop, what happened? Not running in the right thing. I get something relatively symmetric again. So that's one way that the shape of the binomial distribution is related to the parameter p, the probability of success on each trial. Now we're also going to look at what happens if we change the number of trials. So I'm going to go to the 0.7 again, which is where we were before I started just playing with bunch of different values. So here's n equals 10 trials and probability of success p equals 0.7. Remember, we had that slightly skewed to the left distribution. Now if I change the number of trials, so I'm going to copy this down here and paste it, but change now the size from 10 to 20, 20, and I've got 20. You can see that as I increased my number of trials from 10 to 20, just comparing one more time, I went from more skew to less skew. And remember what it looked like when we looked at our 10 trials and a probability of success of 0.3. That gave us this histogram. That's not right. could have redone to do the drops. Hold on. Here we go. It gave us this skewed histogram here. If we were to do this instead with the same probability of success of 0.3, so I'm going to copy this all down. But I change to a number of trials equal to 200 instead of 10. Again, increasing the number of trials from 10 to 200 made my distribution much more symmetric. So the shape of the binomial distribution is related to both the number of trials, n, and the probability of success on each individual trial, p. What we've seen is that for large values of n, we just saw that the binomial distribution will be pretty much bell-shaped even for any value of p, even when it's not close to 0.5. And for small values of n, so relatively small number of trials, like with n equals 10, the distribution looked pretty symmetric when p is close to 0.5, but looks strongly skewed, more and more strongly skewed the farther p is from 0.5. We're going to stop this video here for now and go to a second video to show the next type of calculation that we do with R, which will be quantiles.